All right, get ready for a deep dive into something that might sound a bit like science fiction, but it's got these surprisingly deep roots in physics.
Yeah.
What about the ether?
Yeah, the ether. It's one of those things.
You might think it's just this outdated idea, but the document you sent me, it kind of hints that there might be more to this story.
Yeah.
Than, just on the surface. So let's unpack this.
Let's do it.
So we're diving into excerpts from Aether Validations, and this is by Robert Close.
Okay.
And just so everyone knows, this isn't some fringe theory we've dug up. Close is a retired professor, so...
He's got some cred.
Yeah, he's coming at this with serious scientific weight.
Yeah, this deep dive is kind of like looking through a different lens at physics.
I like that.
A model that could be like a fresh take on some of the fundamental concepts.
A new lens, like putting on a special pair of glasses.
That's it.
All right, so mission is figure out what this ether thing really is.
Okay.
Separate the fact from the fiction and see what unexpected insights we get about physics along the way.
Totally. And it all starts not in the distant past, but with a familiar name, Thomas Young.
Okay.
Back in the early 1800s.
Right.
He was studying light way before Einstein.
Right.
And he found evidence that it behaves like a wave.
Okay, waves, think like ripples on a pond.
Exactly. But here's the thing. Just like those ripples on a pond need water to exist.
Uh-huh.
Young said that light waves also need some kind of medium to travel through.
Okay.
This medium, he suggested, was the ether.
So the ether's like the cosmic pond that these light waves are rippling on.
Yeah.
Okay, that makes sense.
And, this idea, it didn't just disappear.
Okay.
Then comes James Clerk Maxwell.
Okay.
The father of our understanding of electromagnetism.
Now, Maxwell, he's the guy who basically said electricity and magnetism are kind of two sides of the same coin, right?
Yeah, you got it.
Yeah.
But Maxwell didn't just see the ether as empty space.
Okay.
He pictured it more like this lattice, almost like a grid.
Huh.
Filled with particles that he thought represented electric charge.
Great.
It's wild, almost like he got a sneak peek into the quantum world way back then.
Wow. A grid filled with electric charges.
Yeah.
So we've got this ether, this medium for light, that's also this electric grid. Where does Einstein and relativity fit into all this?
Yeah.
Because wasn't that supposed to have debunked the ether?
It's funny. The relationship between relativity and the ether is a lot more complicated than just saying one disproved the other.
Oh.
It's more nuanced than that.
Okay, I am intrigued. Give me the details.
All right.
What did Close have to say about it?
Well, Close actually says that a famous experiment, the Michelson-Morley experiment,
Right.
which a lot of people use as evidence against the ether, can actually be interpreted in a way that supports a certain kind of ether.
Hold on. That's the experiment where they were trying to detect the ether wind, right? Like how your hair blows back when you ride a bike. They thought they could measure how Earth moving through the ether would affect the speed of light.
Exactly.
Okay.
And they didn't detect this wind.
Right.
But get this.
Okay.
The results actually fit with the idea that matter itself might be made of waves in a solid ether.
Okay, now my brain is starting to bend a little bit.
Yeah.
So instead of light moving through the ether, it's like the ether itself is doing the waving. And matter is made up of those waves.
You got it. Think of it like a vast ocean, but instead of water, it's this solid ether.
Okay.
And matter is like the disturbances, the waves within this ocean.
Okay.
So the Michelson-Morley experiment in this framework just suggests that light being made of these waves will always travel at the speed of light relative to this ether ocean.
Right. That's a wild way to picture it. But if we're going with this wave analogy, this idea of a wavy ether, where does gravity fit in? Because Einstein had some pretty mind-blowing things to say about gravity.
Right, and that's where the ether model gets really interesting. Because it suggests that gravity isn't some mysterious force acting over these huge distances, but it's more like a consequence of how these waves in the ether actually behave.
Okay.
Imagine this.
Okay.
Denser areas of the ether where matter is kind of clumped together would make these waves slow down.
So denser areas of the ether are like cosmic speed bumps.
Yeah, kind of. And just like how light bends when it goes from air into water, these ether waves, they would curve towards the regions of slower speed.
Okay.
And that curvature, that bending of the ether waves, that's what we experience as gravity.
So gravity's like a cosmic traffic jam in the ether.
I like that.
The denser areas, they slow things down, cause a curve that we feel as gravity.
Yeah, the very poetic way to put it.
Yeah.
But you've got the right idea. And what's even more wild is that this ether model, this idea of gravity as curved ether, it actually predicted that starlight would bend around the sun. And this was before Einstein.
Wait, really?
Yeah.
So this ether model, this idea that I thought was like, something out of a science fiction novel, was actually ahead of its time.
It seems that way.
That's incredible. I need a minute to process that.
It definitely makes you rethink things, doesn't it?
It does. This is why I love these deep dives.
Yeah.
Okay, so we've got light as waves in the ether.
Yeah.
Gravity is like a curvature of those waves.
Yeah.
What about something like spin? That's a quantum mechanics thing, right? How does that fit into this whole picture?
Right, and that's where it gets even more interesting.
So last time, we were trying to wrap our heads around this idea that gravity might actually be explained by how matter, as waves in the ether, creates these curves in this cosmic ocean.
Right.
But we kind of left on a cliffhanger.
We did.
What about these other aspects of physics, like spin?
Yeah.
That's a fundamental property of particles in the quantum world.
Mm-hmm.
Does the ether model, does it even touch on that?
It does, and this is where things get even more interesting. So the ether model, it suggests that spin, that intrinsic angular momentum that every particle has, could actually be a reflection of the ether itself.
Okay, you're going to have to break that down for me.
Okay.
We've been picturing the ether as this ocean with matter as these waves.
Right.
How do we get from waves on an ocean to something spinning?
Okay, so instead of picturing this calm ocean, imagine the ether's more like constantly swirling, this churning fluid.
Okay.
And now think of particles not as these separate things, but as disturbances, like whirlpools in this swirling ether.
So instead of just like up and down waves, we're imagining like little tornadoes in this cosmic ocean.
That's a great way to put it.
Okay.
And the ether model, what it says is that the spin we measure for particles
Right.
could just be a consequence of the ether's own swirling motion in that region.
So it's like the ether itself has a spin or angular momentum, and those little tornado-like things, the particles, are just kind of tapping into that property.
Exactly.
Right.
It's almost like a way of connecting this classic concept of angular momentum to the quantum world of particle spin.
Okay, that's a pretty elegant link between the very large and the very, very small.
Yeah.
But, things get really weird in the quantum world, right?
You know.
We've got wave-particle duality, the idea that these particles can act like waves.
Right.
Does the ether model, does it have anything to say about that?
It does. Remember those mind-bending electron diffraction experiments by Davison, Germer, all those guys?
Yeah.
Where they shot electrons at a crystal?
Yeah.
And instead of seeing them go through like little bullets, they saw these wave interference patterns as if the electrons were spreading out like ripples on a pond.
Right, I've seen those patterns. It's like each electron went through two slits at the same time.
Yeah.
Even though they should only be able to go through one. It's so weird.
It's totally counterintuitive.
Yeah.
But if we think about matter as being fundamentally wave-like as disturbances in this ether,
Right.
then it's not so strange anymore.
Okay.
Those interference patterns just show us the wave nature of matter doing its thing.
So instead of these electrons acting like bullets that somehow go through two slits at once, they're acting like waves. They're spreading out. They're interfering with themselves because they're part of this bigger ether wave.
Exactly. It gives us this way to visualize and make sense of one of the most puzzling aspects of quantum mechanics.
Okay.
But the ether model's connection to the quantum realm, it goes even deeper than that. Do you remember the Dirac equation?
Vaguely. It describes particles with spin, right?
Yeah.
And it predicted antimatter.
You got it. One of the cornerstones of modern physics.
Right.
And here's the mind-blowing part. Close points out that the Dirac equation, this cornerstone of quantum mechanics,
can actually be derived from this classical ether model.
Wait. Hold on. You're telling me this ether model, that we thought was outdated, might actually be the key to one of the most important equations in modern physics. An equation that's like at the heart of how we understand the universe today.
It seems that way, yeah.
This is incredible. I love these deep dives. This is why we do them.
That's right.
But we've covered a lot.
We have.
Before we jump into how this ether model deals with things like parity and antimatter, which I know we have to get to, let's take a minute to let everyone process.
Yeah, the idea.
All right, so we're back, and we're diving right back into this ether.
Right into it.
Before the break, we were floored to discover that this, supposedly outdated model might actually be the key to the Dirac equation.
Which is like this cornerstone of modern physics.
Huge.
We left another mystery hanging.
Yeah, the parity. It's like this deceptively simple concept, but it leads to some really, really profound questions about, the universe.
Because from what I remember, it's all about symmetry. right? Like if you flip something around, does it still look the same? Like a mirror image?
Exactly. And in our everyday world, things are pretty symmetrical.
Yeah.
But in the quantum world, things get a little weirder.
Weirder how? Give me an example.
Okay, so take your hands, for example.
Okay.
Hold up your right hand, and now picture flipping it like it's looking in a mirror.
Okay.
You get a left hand.
Yeah, obviously.
Right. So in the quantum world, some particles, when you flip them like that, they don't quite act like they're mirror images.
Okay.
And this is where the Aether model gives us a really interesting perspective.
All right. I am hooked. How does the ether play into this whole mirror image thing?
Okay, so remember, we're thinking of matter as waves in this ether ocean, right?
Right. Yeah.
Now, not all waves are the same.
Okay.
Some waves, when you flip them,
Yeah.
they look exactly the same.
Okay.
Other waves, when you flip them,
Yeah.
their flipped versions are different.
Okay, I can picture that. Like a simple up and down wave, you flip that, it looks the same.
Right.
But a more complex wave, it's going to have a totally different shape when you reverse it.
Exactly. And the ether model basically suggests that this difference in how waves behave could be why some particles and their antiparticles are distinct.
Okay, so you're saying these kind of wonky particles, the ones that aren't symmetrical, they're not just breaking the rules for fun.
Right.
Their weirdness is like reflecting something deeper.
Yeah.
About how waves act in the ether.
That's the idea. It's like the ether itself is kind of influencing how symmetrical or non-symmetrical the universe is.
That's crazy. It's like the ether is giving us this whole new way to understand not just like individual particles, but like the fundamental fabric of reality.
Exactly. And it gets even more interesting.
Yeah.
Because the standard model of particle physics, the one we use now to describe all those tiny particles, it has this rule about parity.
Okay.
It says that if you flip everything,
yeah,
every bit of matter, every force, the laws of physics should still hold true.
Okay, so total symmetry. Got it.
Yeah, right. But the ether model, because it's all about waves, it suggests that true mirror image processes might only happen if you don't just flip things left to right, but you also swap matter for antimatter.
So instead of just flipping my hand, it's like, I need to swap it for like an antimatter hand.
You got it.
For a real reflection.
Yeah. It's like the ether has this different kind of symmetry in mind.
Okay.
One where matter and antimatter are like fundamentally linked.
My brain is officially tied in a knot.
It's a lot to take in.
It is. We've gone from these light waves rippling on a cosmic pond to gravity as this cosmic traffic jam, all the way to like the nature of antimatter.
Right.
It's amazing how this ether concept, which I'll admit I thought was just in the history books, could be connected to so many important parts of physics.
And that's really what Robert Close is getting at in this paper.
Okay.
He's saying that physicists, we need to revisit the ether. Yeah. It might not be disproven after all, and it could give us this more intuitive framework to make sense of these really complex ideas.
I like that.
Yeah.
It makes you think. Because we often get so caught up in thinking about science as right and wrong answers.
Right.
But this deep dive has been a great reminder that sometimes it's more about having different tools, different ways of looking at the universe, you know?
Yeah, different perspectives. The ether might not be the be-all and end-all.
Sure.
But it's a really cool example of how a concept that seems outdated can still give us valuable insights.
It's true. And who knows what other breakthroughs we might be missing out on if we just dismiss ideas because they're old.
Right.
So to everyone listening, the next time you come across something that sounds kind of out there, don't be so quick to dismiss it.
To keep an open mind.
Yeah, take a closer look. You might just discover a whole new way of looking at things.
That's what it's all about.
This is The Deep Dive, signing off. Keep those minds curious, everyone.